Hi, everyone. My name is Abigail Hammond, and my presentation is titled From Voltage to Visible Light, Investigating the Bandgap Energies in LEDs. LEDs are something that we see all the time in displays, traffic lights, flashlights, and electronic devices, but the color of an LED is not random. It is controlled by the energy structure of a semiconductor material inside the diode. The main idea of this lab is that LEDs convert electrical energy into visible light. The energy of that light depends on the band gap of a semiconductor. So by measuring the color, or specifically the wavelength of the light emitted, we can estimate the energy difference involved in producing that light. This makes LEDs useful not only as a light source, but also as a way to connect visible light to a measurable physical property. The goals of this experiment were to determine the active band gap from the LED emission wavelength, determine the intrinsic band gap from the voltage temperature data, compare the two methods, and relate the band gap values to the material composition of each LED. The first hypothesis was that the LEDs with shorter emission wavelength would have larger larger active band gap energies. This is based off the equation E is equal to 1,240 over lambda, where the energy and the wavelength is inversely related. So we expected blue and green LEDs to have larger active band gaps than yellow, orange, and red LEDs. The second hypothesis was that as the temperature of the diode increased at constant current, the measured voltage would change in a predictable way. This voltage-temperature relationship should produce a linear graph that can be used to be able to determine the intrinsic band gap. This figure shows the basic energy structure of a semiconductor. At the bottom was a valence band, where the electrons are normally located when they are not freely moving through material. Above that is the conduction band, where electrons have enough energy to move and contribute to electrical conduction. The space in between those bands is called the band energy gap, or EG. This is the amount of energy an electron needs to be able to move from the valence band to the conduction band. The size of the gap is what separates conductors, semiconductors, and insulators. Conductors have a little separation between available energy levels, so electrons can move easily. Insulators have a very large band gap, so the electrons cannot easily move into the conduction band. Semiconductors are somewhere in between, but basically, which makes them basically useful because the electrical behavior can be controlled by temperature, doping, and applied voltage. The figure shows the basic idea of the p-n junction. So on one side, the n-type semiconductor, which has extra electrons, and on the other side is the p-type semiconductor, which has holes in places where the electrons are missing. But when the p-type and n-type regions are joined together, they form a junction. By itself, this junction creates a barrier that affects how the charge can move. But when the LED is forward biased, meaning that the voltage is applied in the direction that allows the current to be able to flow, the electrons from the n-type region and the holes in the p-type region are pushed together toward the junction. And when the electron drops into a hole, recombination is able to occur. The electron loses energy and the energy is released in the photon, and that photon is the light emitted by the LED. The important connection here is that the energy of the photon depends on the energy difference involved in the recombination process. So the p and n-type junction is not just allowing current to be able to flow, but is also creating conditions in which electrical energy can be converted into light energy. So band gap energy determines LED color because shorter wavelength light has higher energy and longer wavelength light has lower energy. So blue light, which has a shorter wavelength, corresponds to a larger band gap. Red light, which has a longer wavelength, corresponds to a smaller band gap. And that is why the expected trend is blue having the highest energy, followed by green, yellow, orange, and red. This trend is what I looked at in the optical portion of this experiment. In this experiment, we measured two related but different bandgap values. The active and optical bandgap comes from the emitted light, and it was calculated using the peak wavelength from the emission spectrum. This method was directly connected to the light-producing region of the LED because it tells us about the energy of the photon being emitted. The intrinsic bandgap was determined differently. It came from the electrical data, specifically from how the diode voltage changed as temperature changed. So the active bandgap answers the question, what energy of light is being emitted? The intrinsic bandgap answers the question, how does the diode material behave electrically as temperature changes? Because those are not exactly the same question. The two values are close in trend, but they're not, identical. The material composition also controls the band gap, which is why different LEDs can emit different colors. So from yellow yellow, red, and orange LEDs, the material system is aluminum, gallium, indium, and phosphorus, or alcohol, alginate. In the equation, the X value represents the aluminum fraction. Increasing the aluminum fraction increases the band gap, which shifts the emitted light toward the shorter wavelength and the higher energy. So within that group, yellow should have a higher aluminum fraction than orange and red. In the green and blue LEDs, the material system is indium, gallium, and nitrogen, or InGaN. In this case, the X value represents the indium fraction, and the trend is different here because the increase in indium lowers the band gap. That means that indium shifts the emission toward longer wavelength. So green, which has a longer wavelength than blue, should have a higher indium fraction. This part of the lab shows that the LED color can be tuned by changing the semiconductor composition, not just by changing that voltage. Now, two experimental methods were used during this lab. The first method was the intensive band gap analysis, and in this part, the LED was placed in a test tube with a temperature probe, and the test tube was heated up with a water bath. And as the temperature increased, the voltage across the diode was recorded while the current was kept constant. The main idea of this setup is that the temperature affects the number of charge carriers in the semiconductor. So as the diode is able to heat up, the electrical behavior changes and the change is reflected in the voltage data. After collecting the voltage and temperature, the values were transformed into V over T and 1 over T, which were used to be able to make the intrinsic band gap graph. The second method was the optical analysis. So in this part, the spectrometer, we use a spectrometer and a fiber optic cable in order to be able to measure the light emitted by each LED. The spectrometer produced an emission spectrum, and the peak wavelength was used to be able to calculate the active band gap. So in this experiment, it compares the electrical method and the optical method for estimating band gap energy. This figure shows the combined normalized emission spectra for the LEDs. The x-axis is the wavelength in nanometers, and the y-axis is normalized intensity. The spectrum was normalized so that the peak heights could be compared more easily, even if one of the LEDs are brighter than one of the others during data collection. The red LED appears to have the longest wavelength, while the blue LED appears to have the shortest wavelength, and this matches the expected relationship between wavelength and energy. So this slide, it shows an example of how the intrinsic band gap was determined by the electrical data. The graph plots V over T in the y-axis and 1 over T in the x-axis. This graph is based off the linearized form of the diode equation used in the lab. And once the temperature was converted into Kelvin, 1 over T was able to be calculated. The voltage was divided by temperature to be able to get V over T. The important part of this figure is the trend line, and the slope of that trend line represents the intrinsic band gap energy, as opposed to being able to read the band gap directly from the raw voltage and raw temperature data. The R-squared value shows how linear the data was. The value close to 1, a value of R-squared value close to 1 means that the data fits the expected linear relationship well. So with the R-squared value of 0.999, we know that the idea of the voltage temperature behavior can be used to be able to estimate the intrinsic band gap energy is supported by that data. So this table summarizes the intrinsic bandgap values of the LEDs. Each value comes from the slope of the separate V over T versus 1 over T plots. The main purpose of this table is to be able to compare the electrical bandgap estimates across all the different LED colors. So overall, the higher energy LEDs have larger intrinsic bandgap values than the lower energy LEDs. This table summarizes the optical results. The peak wavelength is taken from the maximum of each emission spectrum, and the active band gap was calculated using E is equal to 1,240 over lambda, or E is equal to HC over lambda. These values follow the expected trend. The red LED had the longest peak wavelength and the smallest active band gap. The blue LED has the shortest peak wavelength and the largest active band gap. This table also includes FWHM values. FWHM measures the width of each emission peak at half of its maximum intensity. This gives information about how narrow or broad the LED emission was. A smaller FWHM value means that more of a narrow wavelength distribution. whether while a larger FWHM value means that the LED emitted over a wider range of wavelengths. So this graph compares the two band gap methods directly. For each LED, one value comes from the optical analysis and one comes from the intrinsic voltage temperature analysis. The overall temperature is similar. Overall trend is similar. The band gap energy generally increases with the red and towards the blue. However, the values are not exactly the same because the two methods are measuring two different aspects of the LED. This difference is especially important for real LEDs because they are not just one simple uniform material. Many LEDs are designed with heterojunction structures where the active emitting region can have a different band gap than the surrounding semiconductor regions. So the disagreement between the active and intrinsic values does not automatically mean that the experiment has failed. It shows that the two techniques are probing two different physical behaviors. LED. This slide shows the estimated composition of each LED. These were calculated through the active band gap values for red, orange, and yellow LEDs. The material was treated as alganic. The aluminum fraction increased from the red, orange, and yellow. This agrees with the material equation because increasing aluminum increases the band gap. And since yellow has a shorter wavelength and higher energy than red, this makes sense that yellow would have a larger aluminum fraction. From the green and blue LEDs, the material was treated with InGaN, and the green LED had a higher indium fraction than the blue LED. This also makes sense because the increasing indium lowers the band gap, which shifts the emission toward the longer wavelength. So the composition result supports the main idea that changing the semiconductor composition changes the band gap, and the changing the band gap changes the color of the light being able to be emitted. So overall, the results supported the first hypothesis. As emission wavelengths decreased, the active band gap energy increased, and this is most clearly shown in the optical data where the blue LED had the shortest wavelength and the largest active band gap, while the red LED had the longest wavelength and the smallest active band gap. The second hypothesis was also supported because the voltage temperature data produced a linear relationship that was used to be able to calculate the intrinsic band gaps. One of the main takeaways from this comparison is that the active intrinsic band gaps should not be treated as the same exact measurement. The active band gap is tied to photon emission and the LED, while the intrinsic band gap is tied to the electrical behavior of the diode as the temperature changes. So together, the results shown that both emission color and electrical behavior can be used to be able to understand semiconductor materials, but each method gives slightly different information. So there are several sources of error, possible sources of error in this experiment. From the intrinsic analysis, one major source of error is the temperature equilibration. The temperature probe measured the temperature near the LED, but the LED itself may have not been exactly the same temperature at the exact moment. So if the water bath heated too quickly, the voltage data could reflect the thermal lag instead of the true diode temperature. Another source of error was selecting the linear region of the d/t versus 1/t plot. Since the intrinsic band gap comes from the slope, any points included outside of the stable linear region could change the final band gap value. For the optical analysis, spectrometer alignment could have been affect the intensity and the shape of the emission peak if the fiber optic cable probably was moved a little bit too close or was not aligned directly or consistently with the sensor. The peak intensity and the FWHM values could have been affected by that. There is also some uncertainty in determining FWMH because the half maximum points may fall in between the measured wavelength values and requires like some estimation or interpolation. Yeah, that is the end of my presentation. Thank you for looking, guys.